So it should be starting soon. Awesome. We are live and we will wait about 2 minutes for people to join us. But I see people are already trickling in. Awesome. So yeah, I see a lot of people are already trickling in, so we can get started. Hello, everyone.
Sure.
Yeah.
Sure. Should we go? Are we all ready?
Yeah.
Jason,
Yeah, we're all ready. So hello, everyone. It's my distinct pleasure to welcome the IonQ applications team to the second event of iQuHACK 2023. We've hosted IonQ in the past, and it's always been a pleasure. And they have a really exciting challenge planned for almost 1.5K remote participants. So yeah, this is really exciting to have you all here. And let me just hand it off to Dawei to kick off the talk. So please take it away. And please feel free to drop questions in the Twitch, and I'll be interrupting y'all with the awesome questions that we get on our Twitch. So please take it away. Thank you.
Thanks, Shantanu. Hi, everyone. Thanks for coming to our presentation. It's a great pleasure to come back to iQuHACK hackathon. Today, we're going to give me and my colleagues, 3 of us will be giving a presentation covering the physics, or should I rather say intuition, of ion trap quantum computers, what this looks like, to demystify it. And then Jason and Shayoni, they will talk about quantum machine learning, general concept of machine learning, and some very exciting example of what you can do, what people have done, what we have done using quantum computer or ion trap quantum computer. Okay, so first of all, because we're representing IonQ, we're always required to give a disclaimer, but I also know cool people don't like disclaimer. So I have my very special way of doing it, but with you, don't think it's uncool or don't even realize it. So you ready? Here we go. Disclaimer, all material used in the slides are accessible for general public. Interpretation, projection in the talk only represent personal opinions. All right, you got it? Okay, I bet you didn't, but technically we did it. Okay, so part 1, all you need to know about ion trap quantum computer. So first, to some of you, this may be just too simple, but I think it's cool. Yeah, what is quantum computer? In classical computer, we have classical bits. It only represents 0 and 1. With quantum computer, we use qubit. It can represent 0 and 1 at the same times in superposition. However, whenever you look at it or you measure it, it collapses into one of the 2 components, either 0 or 1, if you choose to represent it that way. And the probability of getting each of this one is directly decided by its what we call amplitude. Okay, so here you may think, well, now we can have superposition, and now if we have n qubits, we can have 2 to the power of n states represented all at the same time in superposition, like represented here for the case if we have 3 qubits. We also know that when you use unitary to process information, you can process all the states in the superposition altogether. So you may naturally think, well, great, now I have a giant parallel machine whose power scales exponentially with number of qubits. Well, not really if you think hard about it, because we mentioned before, when you measure it, you stochastically or randomly get one of the components in your superposition. So it's unlike in the classical parallel computing case, you parallelly process everything, you get everything. Now, when you measure it, you still only randomly get one, right? Such a bad news. Okay, so what can we do? The good news is all the superposition not only carries the amplitude that represents the probability of getting the result as measurement, it also carries a phase. And like any other wave object, the phase enable you, or the phase will make them interfere. And if you carefully and insightfully design an algorithm, you can engineer such interference. So in a most ideal way, the superposition interfere that the bad answer all get eliminated, and you are only left with the answer you want, right? So magical. Well, that's everything about oversimplified version of quantum computing, I guess. So, and the ingredients for such interference to engineering algorithm or super well engineered interference is quantum gates. You have single qubit gates like this. You have 2 qubit gates, and all these gates forms universal gate set. That means it would enable you to encode any interference, any algorithm you would want. So our goal to build a quantum computer is to build a system that not only carries the quantum information in the form of superposition to keep it for a long time, but also enable us to operate this type of universal gate set on your information on the qubits. All right. So here are the qubits technology or quantum computers technology out there. Some are more prominent than others. This is back from 2016. You'd be surprised how much things have changed. But okay, let's focus on the ion trap quantum computer. So this is what ion trap quantum computer at IonQ looks like, right? Typical like image, black room, very cool vibe, and white LED. In reality, that's what makes quantum computer get high fidelity. So if you see some picture that doesn't look like this, doubt their fidelity to begin with. Okay, but this is what we have, great fidelity. Okay, if we look back at, if we open the box, okay, this box is probably a size of 3 or 4. Okay, the height of this object is basically a height of a normal shelf that you would have in library or in your room. Okay, so if we open it, at the core of it, you open it, you see a lot of laser photonics, like control box. At the core of it, you will see a vacuum chamber. That's maybe these days a size of a, I don't know, the size of an Xbox controller. I don't know. Yeah. And if you open that thing further, what you see is something like this, a chain of ions trapped in vacuum. Why they form a chain? Because we have to electronically, we have to use Coulomb force to trap the ion, and the ion are charged particles. So they also feel the force repulsion from each other ion. So with all this interaction, with all this force together, they form this kind of crystal. And what you see here is image captured by some CCD camera. And actually, the bright spot you see is not really the ion. It's basically like the sphere given by the image, or should I say the optical limits of your, like the imaging system. The actual ion is even like many order of magnitude smaller than the globe you see here. Okay, so we trap an ion like this. What does it actually mean to run quantum circuits on these ions? Here I have another very cool video for you. When we run quantum circuits, everything we do with ion are essentially operated with laser. So as we run through the gates, we basically beam the ion with the gates, and you see the ion will shake a little bit, right? That's how the information are passing between ions. And when you finish everything, you use another laser to read out. Okay, that's not captured here, but anyway, to say it quick and loud, I guess one would say running quantum computation on ion trap quantum computer is essentially, you can think, because basically it's quantum, so everything has to be timed perfectly. So I personally think it's perfectly fair to call it a symphony orchestrated or conducted by laser and ions, or fun party anyway. All right, so let's look at all the ingredients. First, we have to get ion, right? Ion there, like just like kids. If you let them go free, they're just running like crazy on the playground. So you literally have to trap them with electric field. What enables you to do that? You'd be surprised. Traditionally, you have like giant electrodes, not giant, just like needle-sized electrode. You put in vacuum to trap them, right? That kind of manual assembly is not really industrial standard, right? So you'd be surprised that these days people have been very familiar with this amazing technology of using stuff very similar to what we use to fabricate CPU to make this kind of surface trap. It looks like CPU, and in some sense it is, but it have a lot of this microfabricated metallic pieces on it. Basically it's electrodes, and we can individually control each of them. With all this control over this electrodes, it enables us to very finely tune the electric field at the ion fields. What does that mean? What does that enable us to do? It enables us to modulate or reconfigure the shape of the ion chain, reconfigure the interaction between the ions within the crystal, right? So here, what you see, there's two images here. These two are the trap fabricated by Sandia National Lab. It's called HOA version, model HOA. This is actually version 2. And here is a IonQ surface trap, right? I guess squeezing another joke, you can see how open the two businesses are according to the resolution of the image. You can see from here. Yeah, well, here we go. Why we choose ion as our qubit, right? They're natural qubits, so you don't need to fabricate them. Just trap them from, well, okay, some peculiar source we call ion source, right? Atomic source. Okay, but if you trap them, they're just there. They behave like a qubit. We use the internal level, energy level of the ion as our qubits. And they are, depending on what level you use, they may be unstable, but they could be extremely stable. In this, in our case, like the very most popular species or qubits we use are actually came from atomic clock, right? So to make a good atomic clock, it has to be very accurate, very pristine, very finely controlled. That's why we choose it to make our qubit. And these days, as you can see from this publication, if you do everything, engineering everything well, you can easily get to 1 hour of coherence time. What is coherence time? Coherence time is basically how well you can keep the information in your qubits. You store information in your qubits, you store the phase in your qubits, and if you don't control it well, the information got lost over time. But the coherence time is basically quantify how long you can keep it. So with 1 hour, or I mean, this is with super fine engineering. With normal engineering, if you just want to give a shot, but not give your best shot, if I may put it that way, you can get to like 10-second coherence time. And that corresponds to 100K 2-qubit gates. So with from the perspective of modern technology, with modern quantum computing technology, that's way more than enough. Okay, question, Anthony?
Yeah, quick question.
Yeah.
We have one question on the fabrication behind these ion traps. Do you use standard MEMS technology, or what goes into fabricating these traps?
That's a very good question. I first say I'm not an expert in that at IonQ, or actually just in general, fabrication is a very, very delicate technology, and people have invented many very genius solution there. But as far as I can tell, from a very high level, it's very similar thing, right? You do lithography, you put on your mask, and you deposit layers onto it, and you etch some layer away, and you put another. So this overall, the procedure are very similar. But I think there's some technical specs that basically are just required differently, comparing with if you would fabricate a CPU. So we require different, like for example, the material we would use is different from what you would do for a CPU, right? And the mechanical strength. So that would require different manufacturing or fabrication procedure. So let's get down to the detail. But if you look at a very high level, I'd say it's similar, but I'm not the expert. So, don't blame me if I abuse the concept.
Absolutely. Thanks for that answer. Another quick question. What are some advantages of the ion trap architecture over other architectures, for example, the superconducting circuit architecture?
Oh my God, that's a very good question. You know, there's so many. I can spend whole day just listing them. Actually, we got training. We got trained to do that. Anyway, I'd say, to be very honest, right? You're very smart. I think none of you would be convinced if I just say one is better than another. So I think these days, probably a more fair statement, you can think it as, you know, nowadays people build particle accelerator, right? You say if the LHC is the best, why would we build any other particle accelerator, right? I've been to one of the talk. Basically, the answer or the response is just like, you know, all this different accelerator enable you to experiment with different configuration, or we enable you to explore different regime, right? So you build different ones. They're designed in differently. They each have their advantage. I think it's the same here. You basically, from the algorithm perspective, you'd basically be looking at the coherence time, how long you can keep information, the fidelity, the number of qubits, and the connectivity. All the technology, basically, if you put all this, like the thing I said, into a map, all different technology basically lands at different spot on those map. All right. Back to directly addressing this question. So from that perspective, where is ion trap landing at? I think ion trap lands at high fidelity, not as much qubit as some other technology, but very strong connectivity. We have auto connectivity. And so with that whole landscape, I think this place is where we are at. And this enables us to explore some very specific algorithm more efficient, more effectively than other technology.
Awesome. Thank you. Final thing is just a comment. I think people are a big fan of all the jokes that you're inserting. So.
Oh, really?
Yeah.
Really, thanks. All right. You know what? I may also get sued at some point for making this joke, but you know,
Okay.
It's worth it. Cheers.
Cheers.
Yeah. All right. Okay. So, you know, as much as you may hear from people that quantum computing is entropy-free computing, well, you know, that's kind of nonsense, right? Because any computation you essentially do enable you to get information, right? So it has to involve some entropy in there, the change of entropy. So here, two things. One, detection. When you detect qubit like collapse, right? So how we detect? Okay, I basically just want to say there is a detection. It's important. It has entropy in there. So what do we do to detect qubit is we use this state-dependent fluorescence. We shine a 370 nanometer light on the qubit, and we call this one of them, this one state, this zero state, right? The laser only resonates with this one. So if it's in one, the ion flash, right? Okay, and we use a very finely aligned fiber array to capture the fluorescence from each ion. Here, what you see here, just like array of ion, an array of ion is an array of optical capturing, like imaging system, right? So here, you read out whether they give fluorescence or not, depending on the number of photons you captured. If you have photons, you say they're one, otherwise zero. Okay. Another interesting procedure is qubit initialization, right? Qubit can be in 0 or 1. If you any entropy-free procedure like unitary operations would not enable you, would basically coherently would enable you to trace where the qubit state come from where you end at. Anyway, I just want to say here, this is an entropy. This is a procedure which involves entropy, and what you do to initialize when, no matter whether you are in 1 or in 0 or to 0, is you do this thing called optical pumping. Basically, you have this 2 energy level, right? So you turn a lot of transition on. So to the point that every like energy level are coupled. So the ion can be excited and they can decay, but this 0 state is left alone, right? So every state can be pumped away. The population can be pumped away from all possible level, except this one. So you'd have ion like slowly decay if by any chance they decay onto this 0 state. They stay there, they're trapped there because only this state is not coupled with any other state, right? So this is what we call optical pumping. And that's how we initialize every qubit state, no matter where they start with, into 0. Okay, and we use this very high power 355 lithography laser to drive qubit transition, to drive coherent quantum gates, right? And I have to say, this is a particularly good choice because this is also a very mature technology. It's used in the lithography like industry for a long time. And this also, I want to say, this particular wavelength is only particular for one type of qubits, ytterbium 171 qubits, and you have many other qubits to choose from these days. Okay, and how do we drive 2 qubit gates? And this enables us already to drive 1 qubit gates, right? Because it enables us to interact with the internal state that we use as our qubit state. All right, so to drive the transition, the math is very complicated. You can look at all this paper, but if you just want to hear me hand-wavily talking about it, it's basically you use a laser to pass information. This laser, if you have some detuning on the laser, it not only drives the transition, but also takes a bit of momentum from the motion of the ion chain, right? The motion shared by all the ions. So by doing that, you can effectively, essentially, or virtually, you basically pass the information from the internal state of the ion to the motional state shared by the whole chain. And because they're shared by the whole chain, now if you want to get the information out of the motional state onto a other qubit, you can do that just exactly again by shining a laser on it, right? So this whole procedure, looking at together, you basically pass information from one qubit to another via this shared motion, which we sometimes call it motional quantum data bus. So this is basically using a data bus to pass information from one bit to another, and by definition, it's 2 qubit gates, right? So this is what we do. And how do we address each single qubit? There are several different ways. Traditionally, the people has been very familiar with is to first split one laser beam into many laser beams, and you'd use something known as acoustic optical modulator to control each of the beam, right? To turn them on, turn them off, or you can also use what we call acoustic optical deflector to deflect the beam onto the ions you want. Okay, so one more operation we need to make the universal gate is what's known as our Z operation, Z rotation. So it's basically enable you to adjust the phase of the qubit. And what is the phase of the qubit? Essentially, it's really just what your qubit think its phase is, and the difference between the qubit phase and the clock you use to track it. So here why I put this image, because it's only the relative phase that's matter, right? Just like you are on the train and another train is going like in the opposite direction, you don't know whether you are going or the other train is going. It's all the same. For the ion, you can set the clock or you can move the ion phase. So what we actually do is we adjust the clock that we have to keep the phase of each ion. That means it's all done virtually by just keeping the phase. So it's at this stage, it's the most noise-free operation that you can have on the ion trap quantum computer. And as far as I can tell, it's the same for most of the other quantum computing technology. All right, to summary, ion trap quantum computer is great, blah, blah. Yeah, we have identical and natural quantum qubits. They're perfectly isolated. The whole chain are reconfigurable. They're auto connected and they have a long lifetime. Here we go. And we go to the part 2. I'll pass the mic to my colleague, Jason.
Yeah, thanks, Daiwei. Yeah, so hey everyone, I'm Jason, also a member of applications team at IonQ. So here, Daiwei just gave a really nice introduction about how the technology works and how, you do quantum computing on trapped ion quantum computers. So I'm going to talk about how we could actually use these to do, implement some algorithms. As you know, there's sort of lots of different types of algorithms, different classes of algorithms that you could run on quantum computers. Here I'm going to narrow the focus down to just what's sort of known as quantum machine learning, which is still sort of a very broad topic. Okay. Yeah, so as you know, like machine learning state-of-the-art technology right now, used for all sorts of different problems. Here I'll mostly think about it in terms of like machine learning for image processing based tasks. Of course, it could be much broader, and it's really quantum machine learning is like classical machine learning, some framework for solving data-based problems. Image classification, object detection, 3D object detection. These are like the types of things that people do with classical machine learning models. And they're very, very successful, right? But there are issues that may become more apparent, as the technology progresses, as we want to do more complicated things, that where classical machine learning models struggle, hopefully, quantum machine learning models could come in and provide some advantage for these tasks. Basically, classical machine learning, it's a framework for, data-based optimization of some model to accomplish some task, right? So that's very general, but the field is very, very general, right? There's three basic ingredients that you have. There's data of some form. You have some model, which is parameterized, which processes this data. And then you have some loss function, some cost function, and you want to optimize, right, this cost function. And then, ideally everything works out, and whatever the function you're learning on your data will be able to be applied to some unseen data on the real world, right? So for like generative modeling, where you just have some input and you want to draw a picture, the data that you're training on is going to be, just the pictures, and your output will be, some probability distribution, some class of pictures that you want to draw. For classification tasks, your data set is going to be, this is like supervised learning. It's going to be some labeled data set, right? Some images plus some labels. And then your models here, again, there's a wide variety of choices that you have, but you can think of it as like in neural network, some set of nodes that pass information to each other, that have some set of parameters that you want to train, and it'll apply some function to your input data, right? And you're trying to train to, get the function that you want. And then you want to optimize, right? So again, you could optimize this model in different ways, but you could do something like gradient descent to train some cost function. In classification, for example, like this mean squared error or categorical cross entropy are two typical examples of cost functions that tell you how well your model is doing this classification, and you want to train it, to get the best performance to accomplish your task, right? So that's what classical machine learning is. Next slide. Quantum algorithms, are going to be basically, we want to replace the model portion or some part of the model portion of the machine learning algorithm with some quantum model, right? And in the big picture, for at least for near-term quantum algorithms, it's sort of like a different way to do, quantum computing algorithms, which is instead of trying to learn or instead of trying to implement a specific algorithm, Grover's algorithm, Shor's algorithm, whatever you want, we're going to have some parameterized circuit, and we just want to be able to basically learn, the algorithm, right? We want to learn what type of circuit we could apply, which accomplishes our task based on a circuit architecture which has, parameters that we could optimize, right? We're trying to find the best quantum circuit to implement our algorithm, subject to, a fixed type of quantum circuit, a fixed set of gates that we can apply, right? So it's really sort of trying to optimize the resources we have to implement and solve some specific task. So it's kind of tuned towards near-term algorithms. Okay, so that's very abstract, but maybe it's a little bit more concrete. The basic idea is we want to do sort of hybrid computing using what's called the parameterized quantum circuit, right? So this is input into the model portion of the machine learning architecture. We have some classical data set. We're going to do some classical processing on it. And then we want to feed that into a quantum circuit, right? this quantum circuit is going to apply all these operations which Daiwei described, how we do processing of quantum data, using our trapped ion quantum computer. And then we're going to measure some result using this measurement scheme that, again, Daiwei described. And then we're going to take that result, and then we're going to feed that to a classical computer, right? We're going to do some processing, some optimization on that output result. And then we're going to feed that back in, right? We're going to take that output, feed it back in as input into our model, and try and optimize the parameters of our circuit, right? Each gate that we apply has some set parameters that we're going to tune. And we're going to do this to optimize our cost function, right? This is the parameterized quantum circuit model that's prevalent in quantum machine learning. Okay, so what are the different components that go into this parameterized quantum circuit? There's basically three main components, right? And they're all sort of equally important. And just like classical machine learning, you have like a huge variety of, here they are, encoding, processing, and measurement. You have a wide variety of choices that you can make that may give you, different advantages and disadvantages for your specific problem. Okay, so next slide, that way. Yeah. So the data encoding question is, you're given some classical data, right? An image, for example. How do you get that into a form where you could process it as quantum data, right? That's the question. You want to transfer this image into something that you could work with on your quantum computer. We'll call that quantum data. A quantum data, you can think of, it's just a wave function, right? It's a quantum state that somehow encodes the information that was in your original data. There's a whole bunch of different choices, and they all have different advantages and disadvantages. It's actually like maybe one of the most important parts of any machine learning architecture. How do you actually encode this data? The simplest thing you can do is you could imagine making a rotation, a single qubit rotation on each qubit based on, the pixel value of your image. And so here, one qubit is just encoding one data point. Advantage of this is it's very, very efficient in terms of the number of gates you need to apply to load your data, right? Every gate that you apply, especially every 2 qubit gate that you apply, is going to, in the near term, come with some amount of noise that's going to degrade your results. If you could do it with just single qubit rotations, you're very robustly going to be able to encode your data into the circuit. The downside of this is it's very expensive in terms of the number of qubits you have. If you have a quantum computer that has, 20, 50, 100 qubits, and you have an image that has, 1,000, 2,000, 10,000 pixels, this method isn't really practical. You may need to think of something, more advanced to get all that data into your quantum state. I have something here called unary encoding. It's similar, which is just an example. You're trying to load the data point, like xi, into the amplitude of quantum states. But to minimize the circuit depth, you're just going to encode, one data point, a small number of data points into basis states, but not use the whole, exponential sized Hilbert space. If you want to use this whole exponential sized Hilbert space, you could do this thing called amplitude encoding. So here, you're encoding your information in the amplitude of the wave function. And in this sense, with n qubits, you could encode 2 to the n data points into your, quantum state, which really, you could load huge amounts of data. But there's huge disadvantages of this method also. Mainly, to do this in general, you need deep quantum circuits, which might be noisy and might really, really slow down your algorithm, getting rid of any quantum advantage you have from, processing very densely encoded data. So there's a lot of trade-offs, and there's also like a lot of different methods in between these, like in between these two extremes that you could explore. So this is data encoding. There's a question.
Yeah, a few interesting questions. The first is there an equivalent of orchestrating workflows on IonQ's platforms similar to, Qiskit runtime?
That Daiwei, you know.
Looking for my unmute. Okay, sorry. What's the question?
Sorry, yeah. Question is there a way to orchestrate workflows similar to Qiskit runtime on IonQ's platform?
Oh, sorry. I not familiar with Qiskit runtime, but if the person can be more specific about what kind of operation you want to do, yeah, we're happy to help him or help the person find the best way to realize that. I mean,
Absolutely.
architecture behind it is just like any other quantum computer. So I bet there is a way to realize what he or she want to do.
Absolutely. So on a related note, what is the way participants will be accessing IonQ's quantum computers during the challenge?
I think it's via QBraid but I'm not sure. I think we have a technical team that not three of us, but would be able to address this question better.
I think you could ask in the Slack channel, yeah, and whoever, yeah, someone from IonQ will answer. Yeah.
Absolutely. And another question is, we've been talking a little bit about near-term algorithms. One person asked, are there any near-term quantum algorithms for computational fluid dynamics simulation?
Well, yeah, so there's definitely research on this topic. I'm not an expert on the specific algorithms, but there are basically they're based around ones I know about. Like there's some fault tolerant algorithms based around things like the HHL algorithm implementation, HHL algorithm, right? And there's near-term approaches to try and implement like HHL type ideas that could be applied to computational fluid dynamics in some hybrid architecture. These are the examples that I know of. And I'm sure I know a lot of people are interested in this problem. There's probably some literature on, what's been done. I don't know of any like people who have implemented these on quantum computers as like an experiment. But yeah, certainly.
So I can chime in, like HHL algorithms on near term. There are some algorithms, as Jason mentioned. There are some implementations of HHL for NIST devices, but and you can look up their papers. They did on some quantum devices, and those are like modified versions of the original HHL algorithm. So there are existing literature. You can look up papers like NIST HHL, or you can look up related to HHL. There is another one called quantum phase estimation. You can look up iterative quantum phase estimations. So stuff like that.
Thank you. And one final question. For these quantum machine learning applications, people are asking, about loading in data and what are some of the challenges and hurdles to kind of overcome in loading in data for quantum machine learning models.
Yeah. So I mean, that is like what I'm trying to describe here, which is you need some function on your circuit which depends on your input data, right? So this like product state encoding, it's like an angle encoding. It's simple, short depth circuits, but needs a lot of qubits. Amplitude encoding, much longer circuits. Like in general, you would need 1 gate, 2 qubit gate for every data point, like every pixel, for example, in your image. But you could do it with few qubits, right? But this is going to take like, a lot of gates that are much slower to operate than, taking an operation on your classical computer. So that might really slow down your algorithm, and also maybe too many gates based on like the noise level for NIST devices. So you could try and balance these and do something in between. You could also try and do like these dense encoding schemes to get your data into a quantum state that uses features of your data to compress the size of the circuit. Like there's this flexible representation of quantum images, for example, is something that you load some lossy version into the state, like it's called maybe QPixel, that takes advantage of the properties of your data to compress the circuit size. So yeah.
Very cool. And final question. What kinds of training mechanisms do these quantum machine learning models have? Are they supervised, semi-supervised, more reinforcement learning? What are the kinds of models that you see?
Yeah. So I mean, again, it's very flexible. Like there's proposals for all types. I think Shailen's going to talk about a few end-to-end examples if we have time, hopefully. But like supervised learning, generative modeling, unsupervised learning, there's quantum reinforcement learning. You can fit anything into some quantum machine learning framework.
Awesome.
Yeah. Okay.
Awesome. Thank you. Yeah. Please feel free to resume. Thanks for answering those questions.
Yeah. Okay. That way. It's yeah. Okay. So that's the data encoding. The next steps, right? The rest of the algorithm, basically, you have is also requires decisions, right? You want to process this data once you encode it in by applying some set of gates, right? And here, again, you have a lot of decisions. You want your gates to be parameterized in some way, meaning that your rotation angles depend on some parameter theta that you optimize, right? And you also want this circuit to have some generate some entanglement to take advantage of the quantum computer power, right? The power of exponential Hilbert space to hopefully gain some advantage or access some probability distributions that you can't access classically, right? But then you basically choose these gates in whatever way you want, long circuits, short circuits, high connectivity on the qubits, low connectivity of the qubits, make some decisions, put some circuit architecture, and then you're going to measure the output. And again, what you measure exactly is sort of up to you, but you can imagine just measuring like an expectation value on one of those qubits, and that's going to make your prediction. Like this is the simplest case, right? If your expectation value is greater than 0, it's in one class. If it's less than 0, it's in another class. And then you calculate the loss function. You go through all the data. You apply this circuit, which depends on these parameters theta, calculate your loss function, and then you're gonna, calculate like a gradient based on that, right? And then try and update your parameters to minimize this loss function. So that's the quantum machine learning. How do you actually calculate these gradients? Well, that's another, next slide. That's another like complicated topic. These circuits are almost always differentiable, right? So you could calculate derivatives of the quantum circuit to do some like gradient descent. There's something called the parameter shift rule, which means you could calculate, which allows you to calculate this gradient with 2 evaluations of your quantum circuit for each parameter that you're trying to optimize. The issue here is that if you have a lot of parameters, it requires you to run a lot of circuits. So there are ways around this for NISQ devices to try and do hopefully less gradient calculations. There's like different forms of optimizers that you could use. SPSA, it's like a stochastic search through the parameter space, basically, which uses, the number of evaluations you need to optimize is independent of the number of parameters. Here's a couple other ideas, like this particle swarm optimization or Bayesian optimization, just different ways to optimize your cost function, again, that you could incorporate with your hybrid quantum algorithm. And so basically that's an overview of what's involved in quantum machine learning, and I think now Shaioni will finish up with some examples.
Yeah, hi everybody. I'm Shaioni. I'm also application scientist at IonQ. I work with Jason and Daiwei, and both of them have given you a really nice introduction and in-depth discussion of our computers and how you could do machine learning with quantum computers. So let me give you some examples on discuss some papers and some models that have already done these kind of applications. So to begin with, you heard a bit about machine learning models from Jason. So roughly there are these two classes of models, right? You have discriminative models, which basically differentiate or discriminate between your data instances. And then you have generative model, which try to generate new data instances. So the main difference between the two are like one tries to capture conditional probability, like you do in classification, like given some labeled data, what is the, like given some labeled data, you now try to find the label of your test data, right? And then you have generative model where you are trying to capture joint distributions, and you try to capture these very complicated correlations between the different variables, right? So some examples for discriminative models can be convolutional neural networks, which are extensively used for classification purposes. And for generative models, there's a class of model called generative adversarial network, or GANs. And you might have seen them in the context of generating images, right? They are very popular for images. So next slide. Yeah. So here, this is an example of how convolutional neural networks in classical context are used. Like, suppose you're given a data set with images of dogs and cats, and you have to classify another data set between these two classes. So what you do is you load these images onto your neural networks. And this particular class of neural networks has these different layers called convolutional layers. What these basically do, it extracts features or information from your image. And it basically gives you smaller dimensional features, right? So those, you can think of these are extracting the most important information from your images. And then you load these onto a fully connected neural network at the end, which does the classification for you. And then there are these generative models. The GANs are basically, particularly GANs have two parts. One is a generator and one is a discriminator. In the classical realm, both of these are some classical neural networks. The generator basically takes in some random noise, and the discriminator takes in images from your training set. So the generator generates some image from the random noise, and what the discriminator does is it sees this image generated from the generator and says whether it's real or not. And it sees this closeness between the real image and the fake image by some loss function that you design. And based on the output of the discriminator, you update your generator network parameters. So here in this particular example on the right, what you see is you generate images from a data set called the MNIST data set, handwritten MNIST data set, and you supply these images to your discriminator. This is your training set. And the generated ones are your generated images by your generator. So the longer you train and the better your training is, the generated images look more and more like your actual data set. But as you might have heard about this, or what you can imagine is these kind of models suffer from quite some uncertainties or quite some instabilities, right? Let's say. So you can have vanishing gradient, you can have mode collapse, you can have non-convergence. So generative models are, in general, can be hard to train. And particularly, let's say, if you are trying to generate joint distributions or multivariable distributions, it can get very difficult when the number of variables become very large, right? So because of these different problems, and some of them Jason also mentioned during his part, the hope is, can we improve some of these using our quantum models, our quantum algorithms. So next slide. Yeah, so here's an example where, so this was a work that was done in 2021 from IonQ. And this work basically did a classification problem on our trapped ion device. And they did clustering based on classification of these MNIST handwritten images. And it was done on the actual device. So you first, as you have seen, you first encode the data. Particularly in this case, they use the unary encoding, the second encoding that Jason showed. You encode those onto your circuit, and then you calculate the centroids based on the distance calculated between based on this overlap between the quantum states. And these quantum states are where you have encoded your images, right? And on the right here, you see the performance of our device. X-axis shows you the number of classes. So NC denotes the number of classes, and EDS denotes the number of shots. So shots is how many times you ran your device to get the measurement. And NQ is the number of qubits. So what you can see here is classification error. Y-axis is classification error is basically very, very low when you are doing binary classification, which is the first one. And it indeed increases when you go to higher number of classes. And one thing that's not labeled here is the orange one is when you do error mitigation here. So next slide, David. Yeah, and here is an example of quantum generative learning. So the particular quantum model that was used here is called QCBM, or quantum circuit born machine. So why would you think quantum models are good for generative learning? Because these quantum wave functions, they naturally represent probability distributions, in the sense that when you do measurements from them, you are generating different samples, right? So you're sampling from a distribution. And this sampling can be hard by a classical algorithm. And also, due to the inherent properties of how quantum states are, you can generate correlations, complicated correlations, using these quantum circuits, right? So here in this paper, if you look at the last one here, and I think Daiwei was one of the authors, they used QCBM to capture joint distributions between 3 or 4 variables. And Daiwei, could you go to the next slide? Yeah, and the way to do it is in here, like the particular circuit, the one that you see here on the left, is like you have a series of single qubit rotations and 2 qubit entangling gates. And then at the end, you do measurement. And when you do measurement, you're basically generating a histogram. And then you compare this histogram with your target histogram. So in this model, you're not directly loading the data on the circuit, contrary to the classification problem where you're loading the data onto the circuit. So here, your target distribution, your target data, you use that in your cost function. And using the histogram generated from your quantum circuit, you optimize the cost function and then update your circuit parameters. And with the quantum and with the IonQ devices, what you can do is, so when you look at these entangling gates, so on the right, you see how the rotations and the entangling gates look like. The rotations are the Z rotations, X rotations, and the 2-qubit entangling gates. Both of these you have heard in Daiwei's talk. And with IonQ's device, with trapped ions in general, you can do different connectivities. You don't necessarily have to connect only qubit 1 and qubit 2. You can connect 1 and 3, 1 and 4, and you can explore with a lot of these circuit architectures. So with that, I will end our session here. Thanks for your attention, and please feel free to ask questions.
Awesome. Thank you so much for finishing up that 3-part workshop. We do have some questions, so I'll ask them in turn. The first question is about quantum data and really kind of the future of using these classical and quantum computing resources. And the question is what kinds of data are best suited for quantum data? When is there an advantage to storing data as quantum data?
Well, okay, so I think the advantage of these, like, from my perspective, is not in necessarily storing the data, right? It's in the storing the data, like getting using like some sort of quantum memory, getting the data into a quantum state is like a necessary step to do quantum processing on that data, right? Right. So you have some classical data, you want to get it into some quantum memory, and then you want to do something non-trivial with it afterwards by applying a quantum circuit, right? And so then the question is, what data would you want to process quantumly to get some advantage? And that, you know, it's up in the air. Like, it's definitely an area of active research, like what is best suited. There's some ideas, right? Something like information that is sort of naturally quantum is like an obvious place to look for how you could do machine learning on this data and like get some very concrete advantage over a classical method. Other things like image processing tasks, right, or more classical data, you know, it's much more heuristic. You just need to try and see it a lot of the times, but you might think that things that have sort of a lot of correlations that may not be obvious to a classical computer, maybe you could take advantage of this in the quantum setting, could more easily model these types of correlations. So that'll be my answer.
Awesome, thank you. Another question is it possible to use, classical machine learning concepts like regularization, or more generally, classical machine learning concepts in the quantum machine learning framework?
Yeah, I can take that. Yes.
Okay.
So in general, you can. So for example, you'll be adding some additional term to your cost function. Is there any specific kind of regularization that they are thinking about?
I think it was a pretty broad question.
Okay.
So
Yeah, I think regularization is very important, right? In classical machine learning, if I'm not abusing the terminology one more time, it means you regulate some kind of parameter or freedom of your model, right? At least that's my intuition about regularization. So you will see, actually, if you play with any quantum model, restrict flexibility of your model is very, very important in training of quantum models. I guess just like classical model, you don't want too much freedom. You want to inject as much knowledge as you have into your model. This will not only overcome a lot of training issue, a lot of readout issue, a lot of evaluation issue in your quantum model. So I think from this aspect, it's very similar, right? If I understand correctly, by regularization, you mean you're referring to some technique specifically aiming at regulate your model by like some kind constraint, some flexibility according to the knowledge you already have.
Thank you. And the final question they'll ask here, at least, is, in these sort of CPU, GPU architectures, one problem is latency of data transfer. So how fast are reading in and reading out speeds for quantum computers? Is that a big concern, the latency?
Yeah, so I can answer, I guess. Yeah, so it is a big concern, and the read in and read out compared to okay, so it depends on your architecture. So gate speeds though in general across all architectures are slower than classical computing right now, right? So you need to look for some other advantage for why you might want to actually, some concrete reason why you want to use this slowdown to actually load the data and read it out in a quantum setting compared to a classical setting, right? To gain back that speed. But also, this is very important in like I was describing before, if you need a very long circuit to load your data, even though your data is going to be very compressed in a dense amplitude encoding, you have a huge image stored in 10 qubits or 20 qubits or something, it's going to be very slow because you need to apply a lot of gates to load this data in, right? And this could, in some algorithms, especially fault tolerant algorithms, could take away all the quantum advantage that's known to come from these algorithms. But depending on your data, there may be ways to load it in much more efficient ways, right? Much lower depth circuits. And if you could do this, for images, for example, you could gain back that advantage from these slow read-in speeds. So yeah, it's an interesting topic, but and one that's still also very active in research. But
awesome. Well, there are a lot of very interesting questions in this chat, and I think that's because it was a very engaging workshop. So I direct all these questions and all these participants to go to the IonQ Slack channel to continue to ask questions, throughout this event. There is a really exciting challenge planned for this weekend for our virtual participants. So yeah, we'll end it there. Thank you so much to Daiwei, Xiaoni, and Jason for joining us. And again, it's always a pleasure to host IonQ. So yeah, we can end it there. Thanks so much.
all right, thank you.
Thanks, everybody. Bye.
Thanks, bye.